So you can see, right, in the map that we can see one river. So this river is basically a meandering river that has spiral shape. If you see from the top or bird's eye view, it's the plan view. So that's the upstream. Let me just annotate. So water is flowing from upstream to downstream. That is called upstream side of the river, and here it is called downstream side of the river, right? And then we have surveyed the river, right? And here you can see that's the bridge. Here they're proposing, okay, we have to build a bridge here. That's the connecting road. That there should be the bridge. So if we wanna build a bridge there, so what will be the impact on the river? We have to check if the river is morphologically stable or not, right? And what will be, because if we build a bridge, then the river total conveyance area will be reduced, right? Because of this bridge pier, we'll have bridge pier there, and there the river width will be reduced. So then there will be some scouring because of that bridge. So we have to be able to calculate that scour, and then we have to take measure of the banks of the river. If the banks of the river are not stable, morphologically stable, if it changes with time, then definitely we have to do some bank protection work there. We'll suggest that one based on our calculation and survey. We'll do that, but today I'm going to show you here. That is the real world case. So we surveyed this river from a survey company, and they did the survey like this way at 500 interval. They took different reading, cross-sectional reading, using their echo sounding machine and survey instrument. So that's the plan for survey. I'm going to show you that plan. So here it is. Before surveying, they made the plan like this way. And okay, let me just quickly clear that, then you'll see clearly. So that's the plan. So that's the upstream, what is coming from upstream to downstream side. So at the same time, what you have to remember, that is the left bank, you have to keep in mind, and that is the right bank. For HEC-RAS model, it matters if water flows from upstream to downstream, and if you are standing there and if you're looking at the flow, and on the left side, right, the left side it will be left bank, and on the right side it will be right bank. But what we need in this plan, we have to survey such a way that we can measure the cross section from left bank to right bank, from left bank to right bank, because this HEC-RAS model can take, right, it can take the cross sectional value from left bank to right bank, right? So that's what we did here. So the survey company, they just made this plan beforehand, right? That okay, they'll take the cross section here, and at 500, this interval is 500 meter, right? 500 meter, half a kilometer. So they just made this plan, and then they started their measurement from here. So if you, this is the bridge center, and then that is the center line, okay? And here upstream cross section 1, 2, 3, 4. So if you go upstream, your number of cross section is increasing, and CU means cross section upstream. And if you go downstream, then we have D, right? CDS means cross section downstream 1, 2, 3. So number is increasing, you are going to downstream direction. But in the model, you can import this cross section, or you can create the cross section from upstream to downstream. We'll do that. We'll start the cross section from upstream to downstream, and the upstream cross section number will be the higher number, and the downstream cross section number will be lower. So that will automatically be fixed. If you provide two number, 1 and 2, then 1 will be the downstream and 2 will be upstream. So that is the notation. The model, the modeling software HEC-RAS, it will automatically understand that the minimum value is the downstream cross section, and the maximum value is the most upstream cross section. And the cross section you are inserting, whether you are inserting right and wrong, it doesn't matter, but the model will assume that okay, you are inserting from left bank to right bank. Okay, the maximum value will be most upstream, and the minimum value will be most downstream, and the cross section we are inserting, that will be from the left bank to the right bank. So that's why now we have idea about which one is left bank and which one is right bank, which one is upstream, which one is downstream. So at the upstream cross section here, we need boundary condition, right? So we'll provide Q, flow rate or discharge, as boundary condition, and at the very downstream, if it is there, we'll provide water level, right? So for Q, we'll calculate 100-year return period of the Q. So we have historical data from different observation stations, and then we'll use Gumbel distribution method, Gumbel extreme distribution method, to calculate this 100-year return period of flow rate, and same for water level. Then if we use, that means we are designing the breeze for 100-year of return period. If there is a flood that has a return period of 100-year, then the breeze has to be survived, right? The breeze will survive for this type of flood or rainfall event or flooding event, whatever it is. So that is the condition. So we have to be able to calculate this one. So these are the input data. Today I won't show you that how to calculate Q and W, but in the next tutorial I'll show you how to calculate 100-year return period, flow rate, and water level as well. These are called statistical analysis. I'll show you that using Gumbel extreme value distribution method. So today I'm going to show you how to even create the geometry from HEC-RAS. If you have any survey data as Excel file, we have to be able to create the geometry. And then I have this data ready, so I'll insert this data, and the model I'll run today, it will be steady state, so there won't be any time series. The one value of Q will be fixed for the entire time, and one value of water level will be fixed. Okay, so that's that. Okay, I'm just clearing this drawing I have, and I'm going back to my model setup. So I have this software package open, right? Let me just introduce you what we have here. So here it is the open. If you have already developed your model and you can open it, you can click there and it will open, and this button, it will save the model. And here you can even open the editor of geometry. This way, if you click there, it will open, and then we can insert our cross section. I'll show you shortly this one. And you can do the same thing from editor. You can go to geometry. So same thing you have as a menu bar, and same thing you have here in the as icon. Okay, and next thing, it is the, if you click on that, it will show you what it is going to do, right? This is geometry, that is that, that is that, and you can, this is the 3D. If you want to see any cross section, this is the RAS mapper, it is showing here, right? RAS mapper, and it is editor, steady flow editor, and you can go there, you'll find that same menu. The same thing, I'll show you which one is doing which thing. And if you want to see the profile, you can click there. If you just put your cursor there, it will show you the name of the menu or the plot, right? And at the same time, if you want to run steady state, steady means the flow rate, water level, velocity, if it is constant with time, then it is called steady state flow condition. So that's why they are showing that someone is running on a flat surface, there won't be any change. But here, that's why it is called steady state. It is the running. If you want to run the model, if you click that button, it will start running that one. And if you want to run the model as unsteady, that means if flow condition, water level, or velocity will change with time, then it is called unsteady flow condition. So that's why you can see someone is running on a surface or on a wave that is changing, right? So same thing for here, it is the unsteady, quasi unsteady sedimentation. You can see some dust, and here it is also dust, but the people or the person is running on a flat surface. That means it is water quality, and you can see the color, right? Water quality model. And that's that. If you want to see the result as a tabular format, you can click on that. It will give you the summary of the data. I'll show you after running this model, and there are other options to display and extract the plots and other information. I'll show you that. So since I'm gonna set up this model from HEC-RAS, so just follow this step. What I'm going to do, at first click on file and then new project, and when you are done, you have to specify where you want to save your project. So here I'm not going to save in my C drive because it will kill my space. I'm going to select another drive, D drive, and I'm going to direct it to there. Okay, inside that HEC-RAS I'm selecting this directory and give the title as what? So this will be by the name of a breeze. Okay, breeze model, because ultimately we are gonna finish this breeze model, breeze scour. Okay, breeze scour model, this is the name of our project. If you click OK, it will create this name, and you can see, and what will be the unit system for the time being. Okay, click OK, not a problem. So here it is, we have the project name, and if you want to change the unit, because we'll use our SI unit, so here you can see by default it's customary, because this software they developed from American US Army, so that's why in US or in America they use US customary unit, means feet and pound system, but we are not gonna use that, right? We have the survey data in meter, velocity in meter per second, and we have the flow rate or discharge as meter cube per second. So that's why I'm going to change it. If you click options and then unit system, then you have the option to change it. So we are going to change it to system international. Okay, then we have the unit. See, you can see we have SI unit. Now what you have to do, you have to click there, view or edit geometric data, or you can click there, edit and geometric data. It is the same. Okay, it's gonna open this window, and what you have to do, let's look at the map. So we have this. Okay, so this is the upstream and that is the downstream. So what is coming from upstream to downstream? So at first what you have to do, without thinking, can you see that? Yeah, river reach. Okay, you have to draw the river reach. What is a river reach? A segment of a river is called a river reach. Okay, so if I click there, so it is activated, I can draw the reach. And what I'm gonna do, I can even draw this way a line, straight line, it doesn't matter. Okay, and double click, we have one reach, and you can write the name. I'm gonna give the name as river. If you know the name of the river, you can write the name, and if you know the segment of the river, right, you may have a big river, right, very long, and then you will have some tributary, distributary, so that these are the reach of a river. So then you can write the name. Okay, I have the big name, and this is the tributary of the river, that means it is the reach. But for this case I'm giving the river reach, okay, as reach name. So I have one river, one reach. See, it is showing, because I have drawn this line from upstream to downstream, so it is showing that this is our flow direction. Okay, now I have to insert that cross section, right? The river means cross section. So here, see, if you click there, it will open the cross sectional editor. We can add cross section. So if I click on there, we don't have any cross section, and we have to create one, and we have the option here. See, the station, this will be the measuring station from left bank. So from the left bank you have to give your changes or the distance. It will be 0 on the left side, and what will be the elevation, you have to put that, and then you have to go to the river, and then you have to measure the elevation. So let me show you how it looks like, the real survey data. So here is the survey data. You can see I already mentioned that we have total 20. Here you can see that we have total 20 cross section, and UCS means these are the upstream cross section, and in the plan you can see the maximum number for this case, because this is the plan. They just mentioned, okay, they will take 12, but in reality they took 17. So the 17 means it is the most upstream, and 1 means it is the upstream of the breeze, right? So our most upstream will be the maximum number of CU cross section. So that's that. See, it is 17 means most upstream, and if you go to 1, it is close to the breeze. And then we have CSDS, right? We have CSDCS. This 1 means it is close to breeze, and 3 means it is away from the breeze to the downstream. So this 3 means it is the most downstream, and the 17 means it is the most upstream. So our total number of cross section is 20. So if I just specify, because in HEC-RAS the way it stores data in DSS system, data storage system, that the maximum number of the cross section they will put it at the upstream, and the minimum number of cross section they will assume, okay, it is the most downstream. So if we create one cross section of at first 2, let me just show you that. At first you have to go to options and then add cross section, right? And before going to do that, let me show you, if I open one file, the most upstream one, 17, we have the plot. So what do you have to do exactly, right? We know we have to do, we have the point, they started the measurement, this is wrong, this should be right bank because I corrected it. This is the left bank. So what they did, they just started, this is the 0, okay, they started the measurement point 0 and here, and they measured the elevation, it is 5.11, and then they just, right, they moved to the river 6.27, and next point the elevation is 3.9, and then they just cross the river, and on the other side that is the right bank, and they are done with that. So they also mentioned, okay, this is the left bank LB and that's the right bank RB, right? This is the cross section, this is across the river, that's why these are called cross sections. So what do you have to do? We have to copy these two column and we have to paste it there. So how can we copy that and paste it? These are the manual job we have to do 20 times. At first we have to create the cross section as a blank cross section. So first go to options and then add a cross section, and it will ask you the number. You have to put the number, any number you can put, but since you know we have only 20 cross sections, right? In total we have 20. So if I put 20, it will be the most upstream, and if I provide 1, it will be the most downstream one. So I'm gonna enter as 20, right? And it is not showing anywhere because it doesn't have any idea where to show, right? And then I doesn't have any idea that what will be my next cross section, because I know that I have 20 cross section, so the minimum will be 1. So I'm giving the 1. And okay, before going to do that, I can even copy this two cross sections, two columns of this Excel file, and that is the trick we have to apply. You can insert one by one, or if you click there, here it is selecting, and then if you paste it, it is just pasting the entire data set. You just copy it, column, the station and the elevation. Okay, then what you have to do, you have to provide these values. So if it is most upstream, then what is the next, right? What is the distance from the left of the bank, from the channel of the bank, and from the right of the bank, the next cross section? What is the distance? You have to provide the distance. So for this case, we know if it is most upstream, the next cross section is located at 500 meter. Since we are using SI unit, so I'm giving 500 and 500 everywhere. So what will be the Manning's coefficient? We are giving the standard value 0.023. We can give that, and in channel it is different, on the bank it is more than that. So in channel I'm giving 0.020, and I'll use the same values for all of these sections because we are selecting a cross section that is mostly 3-4 kilometer, or more than like 10 kilometer, less than that. Okay, so that's it, we're done with this one. So if I click apply, you can see, and at the same time you have to specify the left bank, which one is the left bank. The starting point is the left bank. Okay, I'm copying that and I'm pasting it here. And what is the chainage of the right bank? It is the, that's why in the survey data they mention that which one is left bank and right bank. So it is, for this case it is this one, and I'm pasting it there. If I click apply, it will show you that cross section. See, it is the cross section it is showing. So the good thing about this software package is that you can copy, because each time if you create one new cross section, you have to do the same thing. Because if you know that, okay, your distance from this cross section to that cross section is 500 meter, and your, if you keep this Manning's coefficient for same for all of these cross sections, right? But this will be only changing, and the contraction or expansion, because on the left side and the right side we can keep this as it is, 0.1 and 0.3. These are the coefficient for steady flow, and we have this cross section. We can copy this entire cross section, so it will copy everything, and next time we will only replace these values. We'll keep this as it is. Okay, then our task will be easy. So what I'm gonna do, I'm gonna even create another cross section, but this time I'll create new one that will be the downstream one. Okay, so create new cross section, and I'm giving the name as 1, and it is new one. And since it is the most downstream, there won't be anything, right? That's why this downstream reach length, it is 0 from the downstream cross section. Then it will understand, okay, this is the downstream one. Okay, and then when I'll enter the value for this one, I'll fix everything. So now I have the cross sections, right? If I close it, see, now it's gonna show you what is that. Since we didn't enter the value, that's why it's not showing this line. Okay, but we have, right, we have entered the value for 20 and it's showing the length, the cross section. So we can enter, click again, cross section, and then we can create the dummy cross sections. We can enter, not a problem. We can enter the value. So the 3 downstream cross section of 3, that is the most downstream. Let me copy that and it will show you this one. So which one will copy? This one. The first value is the left bank and the last one is the right bank. Okay, so keeping in that mind, so here it is, click there and paste, and this will be 0, and that is that right bank. So if we click apply, so now we have the most downstream cross section, right? So that's that. If I click or close it, then we can see which one is that one. Okay, even after inserting all these values, we have to specify, okay, this is my cross section. Okay, and then if I open it again, see, you can see, since we are selecting this one, it is showing us, okay, that is my left bank, that is my right bank, and it is gonna show you everything. And you can even scroll from one to this one to that one, this one to that one. See, that is the, if you click this one, it's gonna change to this one to that one, and the red dot means it is specifying where you have the bank line. And this point, you can select your bank line is this one or that one. The surveyor said, okay, this is the bank line because they started with the bank line, right? So that's that. So now what I have to do, I have to insert the intermediate stations, right? So I'm copying this 20, I'm copying this, and then I'll replace this one by one. Let me just copy, option, copy current cross section, and I'm gonna give the name as 19 because the next cross section will be 19, and it is gonna reduce the number from 20 to 1. Then it will show, okay, I have the cross sections from upstream to downstream. See, we have the 19. Now it is same because I'm copying, and then if I copy the current cross section 19 to 18, then I can give 18, right? And I'll replace these values later on, keeping this same, and then it will be 17. These are the manual job, that's why I'm starting from scratch so that you can understand what we need to do. Now what do we need? We have 17, right? We have 17. Now we need to have 16. Let me check if I miss anything. No, we have the list. If you click there, 20, 19, 18, 17, 16. So next we'll have 15, and after that we'll even insert other values as well, and then it will be 14, and the next one will be 13, and then yeah, you can repeat everything. You have a 12, and then once it is done, then the model run is pretty fast. Then it is 11, and then it should be 10. We have 10 more to go, and this should be 9, and next it should be 8. Let me make it fast. And then we have 7, then we have 6, then we have 5, then we have 4, then we have 3, and we are almost done. Then we have 2, and we already have 1, right? So these are the cross sections. If I close it, you can see all these cross sections from 20 to 1, but we didn't even provide it, right? We didn't provide the exact value of cross section from 19 to 2. We are already provided only for 20 and 1. So let me just open it again and select the 2, or no, I'm starting from the beginning, 19, and I'm gonna close the previous 20 and the first upstream one, and then I'm selecting one by one. So the 16, this time it will be the 19. Okay, so that's that. I'm gonna copy, and then we have to paste it. How can we paste it? Because we have to replace this one. Click there and paste it. The first value is that one, and copy this one, and each time you have to replace this one as well, and apply. It is gonna change, right? We are done with this one, and this will be 18, and I'm gonna select that one. These are the laborious tasks we have to do. No way, that is the model setup. It may take few days, it doesn't matter, we have to move. Okay, I'm done with this one. I'm copying this one, I'm pasting this one, and apply. Each time you change anything, you have to apply and then go next. So we are gonna do for 17 right now, and then I'll make some interpolation. So these are the cross sections. It is pretty easy because within 500 meter, if we interpolate right at 100 meter interval, that is pretty quick. That's why you don't need to have, right, you don't need to even spend a lot of money to measure the cross section at 50 meter interval. We don't need that. We can interpolate. This is the option we have, so we can utilize that one as well. And then our model, because we are just focusing on our breeze model, so we don't need to even worry about the cross section that are far away from upstream, only to the survey data. Even we can use DEM data to create any model, but since it is a real case for a bridge design, that's why we spend money to survey this river to make our model perfect as much as possible. And you can utilize this one as well. This is your opportunity, I think. You can see and you can replicate. So these are the real world case. Otherwise, if you see some problem that are really fancy, people are making it without showing anything, yeah, we can set up the model within 10 minutes. That is possible, but it won't help you anymore. Okay, so that is the issue we need to do. So I'm gonna replace this one as well, and I'm gonna copy this one and paste it here. Each time you have to keep in mind, I'm talking and I'm just doing this thing. Maybe I can make a mistake. It is also possible, but since I did this thing many times, so I can even do all together, not a problem. So each time I can copy, I'm just making track of everything. Okay, I'm copying. That's why I'm following some sequential order, right? Each time, see, I didn't change it, so I have to change it, and then I have to click on that and then paste. When I'm done with pasting, I'm copying this one and then I'm pasting it here, and I'm just applying, and then I'm just moving to the next point, and then I'm just opening the next one, 10, right? And then see, I'm copying it. Okay, I'm selecting this 2, and then I'm copying it, Control C, and then I'm going to that one and selecting here and pasting it. Again, I'm copying this one and I'm pasting it here and applying, and then I'm going next, and then I'm just closing this one, because if I keep open, then I won't be able to even track which one I'm copying and pasting. And then here I'm in number 9, and I'm copying it again, because it depends on the river cross section. You can see at the same time how it looks like, right? The same cross section we have here, and we can see we have the same cross section there. I'm copying and pasting at the same time, and again I'm just replacing the right bank, because left bank is always at 0. Okay, so which one is next? This one, number 9. So this is how we can import. There is no other way to import. If you are done with your geometry, then you can manipulate. There are a lot of options to manipulate geometry. That's why this is the most laborious thing we are doing here, right? We are done, almost done. We are done with 10. Now it's 7. 7 means it's the upstream cross section number, not the 7, because we have 2 downstream cross section as well. So we have to even enter those cross sections. So see, that's why the river is meandering and it is changing its length of the cross section, right? See, it is just changing. And if you see, it is half of this. No, you can see here, if I just move this red bar, right, zoom in, you can see the bottom of this. So it is automatically showing that one. So don't think that, okay, we have half of this cross section and we have missing data. It is not like that. So what is next? It is this one. So we are almost done with our upstream cross section. So now what we are doing here, we are just coming from most upstream to the bridge location, right? And then we'll cross the bridge and we'll go to downstream side, and then we'll be done with inserting our cross section. That's why when the river width is less, right, from half a kilometer to 263 meter, then we're just building a breeze so that the length of the breeze is not that long, only to reduce the cost, right? So that's why survey is necessary, or these are called reconnaissance survey. You have to inspect where to build this breeze, and if you can do that, definitely your cost will be reduced. Otherwise, without inspection, without reconnaissance survey, how can you build a breeze? These are the steps you have to follow, and then you will be able to build the breeze, right, with less amount of money. This is called economy. You have to be able to design the breeze using your engineering knowledge and at the same time with minimum cost. So that's why we need engineers, otherwise we don't need them, only to calculate efficiently, economically, and cost effectively. They have to select the building material as it is cost effective, and with minimum cost the bridge should survive, right, at least for 100 years, because we are going to select the return period of a flood for 100 years, and we are designing this breeze for 100 years, so it should sustain up to 100 years. It has to, otherwise there is no engineering. So we have to be able to calculate this. That's why I'll show you how to calculate the breeze pier, because if the breeze is there and if there is some kind of flood that is not even 100 years of return period, but still the breeze is facing problem, so it has to survive with different types of scouring. And this is how we calculate the breeze scouring. I'll show you in this, not today. Today I'll show you how to only run the model, how to display the result, because it is taking too much time to even insert. When I'll be done with this laborious task, then I can show you how to calculate the input value. If you are correctly, okay, if you have your survey data, you have everything, but how can you calculate the 100-year return period? You have to follow some rules, right? You have to follow some guideline. So there are some guidelines. We have to follow this, and once you are done with that one, you can use that value. And why we are just running this model for steady state flow condition? Because we don't need to run the model for unsteady, and the location of the breeze is another point. If there is no tidal condition, if there is not that effect of unsteady flow, means if the flow condition is constant, that is more effective, right? And if you can change it to unsteady, not a problem. But most of the cases, if the run condition is simple, we can do that. Okay, now we can finish the rest of the cross section. So here is that one, so we can copy number. Yeah, I can just close that so that I can even make track of this quickly. Let me close this one, this one, this one, this one, this one, and we have many. See, so yeah, what do you have to do? You have to copy the number 3, right? So if I copy number 3, let's see what we have. So we are done with that one. So keep in mind that number 3 is the number 1. Number 3 is the lowest one, okay? So it will be 1 because it is starting from the breeze section. So if I copy this one, and then if I paste it there, it will be, you have to click there as usual, and then I'm just copying this one. That will be our right bank, and apply. So we are done with that one. We have 2, and then downstream section number 2. Yeah, that one. These are from left bank. You have to keep in mind. And I'm just okay, it should be the next one, and pasting it there, copying and replacing this one, and then apply. So we have the last one. Okay, I think we already, right, we already maybe replaced that one. Okay, let me just check it before proceeding. Not this one, it is not the one I'm getting. It should be number 3. Okay, so That's that. Just make sure that we are on track, and I'm just copying and pasting. Maybe it's the same one I pasted. Yeah, it's okay. So I applied, so we have our cross section. So what do you have to do? We have to save it. How can we do that? Go to file and then save geometry as. Okay, we'll set the geometry as our original geometry, because we'll interpolate, right? We'll interpolate that geometry. That will be our interpolated. So we already saved it, and now if I closed it, right, if I close it, then you'll see we have the geometry here, original one. I'm opening it again here. What I'm gonna do right now, I'm gonna interpolate that geometry with, right, now we have 500 meter distance in between two sections. In between section 20 and 19 we have 500 meters. So I'm gonna interpolate that geometry, and I'm gonna make 100 meter interval. You can use more than that. So how can I do that? If you click there, tools, and access interpolation, cross-sectional interpolation, means within a reach. Since we have one reach, we can even interpolate within a reach. Then it will interpolate every section, or you can even interpolate in between two sections if we specify. We can do that. So since we are interpolating everything, we are selecting within a reach, and if you select that one, see, it is selecting every reach. If you have more than that, you can select from this drop down menu. And what will be the maximum distance between these two sections, right? It will be 100 meter. And what will be the interpolation method that you are going to select? It will be linear interpolation. And then you can select here interpolate, then it will be interpolating. And if you delete it, you can delete that. If you think okay it's wrong, then you can delete the interpolation, and it will only delete that interpolated cross sections. If you close it, you can see the interpolated sections. Okay, and if you want to delete it, if you think okay I made a mistake here and then I'm gonna delete it, then you can do that. Go to interpolation and then section and delete it. Okay, then it will be deleted. It will only delete those sections. I'm gonna do it again to show you the processes we have. It is only 100 meter interpolate and that, and now I'm gonna save it again, save as interpolated section. Okay, instead of original one, because I just preserve the original one so that I can even change whatever I need. Okay, but for any bridge analysis we don't need to do that. Okay, I'm gonna do it. So now we have our interpolated section. We are gonna use that one. What do you need to do right now? We have to even import our boundary condition. So what will be our boundary condition, right? So we have to provide here this section number 20. There we have to provide the flow rate, the discharge, and at the downstream level at 1 we have to provide the water level. Then the model will understand, okay, this is the discharge here, the very upstream, and that is the water level. So it will it will keep that in mind, and then it will calculate, it will solve the equation, the differential equation, and then it will give us the water level, for water level, velocity, and flow rate, everything for right at each of these cross sections. So now we have to even provide that boundary condition. So for running any model, we need the cross section or the bathymetry, and then the boundary condition, and then the run condition as well. So for this model we have that. If you click on that edit, and we have the option steady flow condition, so we are going to select the steady flow condition. So if it is steady flow condition, we will have to provide the flow rate here, right? We can do that. And what will be the flow rate for this one? I'll show you how to calculate that 100-year return period. So for this one I'm giving that 55 cms, means meter cube per cubic meter per second. You can see that here. And if you want to change the name, you can add more profile. You can add as many as you want, up to 32,000 profile you can add at the same time. But we don't need that. In future videos we'll add only 3-4 profiles, and we can compare different conditions. If you have 100 year return period of flood, if you want to analyze 50 year, 500 year, then you can add all this profile all together, and you can run it, and you can check which profile is giving you right what will be the water level, maximum water level, and other velocities. Then based on that, if you don't need to even select that 500 year of return period, then you can decide. There will be based on the difference, right, or the height of the water level, then you can decide which one you are going to select. Because if you want to select 1000 year and it won't affect that much, then you don't need to select that one, because it will increase the construction cost of the bridge. So I'm going to select only one profile for this time. And then if you want to change the name here, what do you have to do? You have to even select there, okay, reach boundary condition, you can do that. If I click on there, and we have to even provide the boundary condition, downstream boundary condition, okay. And we can, what we can do, we can even select this one, we can even add, see, add a flow, change location. If we have two river connecting together, we have a, or even you have different flow rate that is contributing, you have any tributary, distributary, even you can add at which section. If you have any tributary of a river at section number 15, you can select that cross section and you can add that one. In the future video maybe I'll show that, not a problem, but today I'm gonna just show you only one single reach and single simulation, then I'll add different condition as well, okay. Since I'm just inserting everything from the beginning, so it is taking a lot of time, and the length of the video may be even longer than 1 hour. I don't know what is gonna happen today, so we can even do that, okay. So that's that. And if you want, you can even add multiple location. These are the options, and here, from here, you can even change the, edit the profile names. If I click there, even you can change the profile name. I can give you, it is like 100 here, okay, 100 here flow, so that you can track this is for 100 here, and you can add more profile for 500 here, okay. You can add that. And if I want to select that reach boundary condition, okay, reach boundary condition, then what will happen? We need to provide the downstream boundary condition. See, by default it is showing the downstream boundary condition here, right here. So when I'm selecting that downstream boundary condition, you can give known water level, because we have the known water level for 100 year return period, and you can even provide the critical depth. You can provide the normal depth as a slope 0.0025, and you have to calculate that one, or you can give the rating curve, right, and you can even delete everything whatever you have. So I'm gonna give known water level. So I have the water level known. If I double click there, and I can provide that, this is 7.85 meter, okay. So I'll show you how to calculate that one from historical data and from Gumbel distribution method. I calculated this value, and it needs a lot of calculation. I'll show you that how to do that in the next video, so that you can even calculate that one as well. If I click OK, so we have our boundary condition. I'm clicking OK. So we have our flow rate at the very upstream, and we have the boundary condition water level at the very downstream, right? So what do you have to do? We have to even save this, okay. How can you do that? Go to file and then save the flow data. So then you have to provide what is the flow condition. You can give the flow condition as 100, okay, year flood, 100 year flood condition, that's that. And if I save that, so now we have this, see here, steady flow 100 year flood. And then what do you have to do? We have to even provide the run condition. Go to run and select steady flow condition. If it is unsteady, we can select unsteady. In the future video we'll do that. So I'm going to select steady flow analysis, and here we have to select which geometry you are going to run, okay. So I'm going to select, so we have two, I'm going to select the interpolated, and then which steady flow condition you are going to select, or unsteady flow condition. So we have only one profile. I'm going to select 100 year flood, and which will be the flow regime. We know that for river flow it will be subcritical, right? If the flow number is less than 1, the flow is subcritical. So most of the river flow, these are subcritical flows, so we have to select this one. So I'm going to select this one, and we don't need to even select that floodplain mapping, because we are not running a 2D model. When we'll run that, we can do that as well. And then you can provide one short ID as 01, because if you want to change the condition or plan, it will change it. And then what you have to do here, go to file and save plan. Then it will ask what will be the plan name. So I'm going to give the run 1, okay, run condition 01 or run, it's okay, and it will, because we already provided the ID, it's okay. So you have to give this ID, it's already there, and this will be run number 1. And if you compute, if everything is okay, then it will start running the model, okay. Otherwise it will display the problem we have, right? And it will locate the problem where we have the problem at. It will even display the cross-section number. We can even go to that number and we can select it if there is any difficulties or any problem in that calculation. And okay, let me just run it quickly. It will be pretty fast. I'm hoping it's going pretty well. See, there is no error. So run completed, the process is successful. We can see the result right now. So that is, I'm just closing that. See, if I open the geometry this time here, and if I even select the flow condition cross section, we'll see the water level, right? See, now the cross section is filled with water. This is the most downstream one, and if you click there, you can go to upstream, and if you can go to the next cross section, because we interpolated, it is just 19.8, and then it is just giving the IDs, and you can see water is just, we have this water, and you can see the velocity profile. If you want to see the velocity profile, you have to go to options, and then you have to select that variables, right? And then we can see, I'll show you that how to do that. I'm just showing how to even see the result. If you want to see the result as summary, you can click there, the table. It will show you the table values for each of these. See the profile, we have one profile. It is giving you the flow rate. Since it is a steady flow, the flow rate is same for all, and you'll see the minimum, right, the elevation, and this the water surface elevation, right? And if you have any critical energy, it will show that, and this is the energy grade line, okay? And then it is going to show you that slope of this line. These are the slope at that cross section from this one to that one, and the velocity, channel velocity, and the flow area is, these are called conveyance area, and the top width of the channel, right? And it is going to show the Froude number, means it is less than 1, definitely the flow is subcritical. So this is how we can even see the result of this model, okay? You can close it, and then if you want to see the long profile, you can click there. You can see the long profile of the channel, right? You can see that. And if you want to see other, because I'm not going to show you the result analysis right now, I'm just going to show you how to view results, right? And if you can open your cross section from here, right? Cross sectional velocity, we can even see, and here even you can gonna see the variables, which variable you want to see. At present time, it is showing the water surface profile and everything, right? It is showing this way. So in the next run, I'm gonna change it because I want to see the velocity distribution here. That's why what I have to do, I have to change the run condition a little bit. Then you'll be you'll feel that okay, that is the thing you want to know. So I'm gonna select the steady flow condition. No, here from run steady flow analysis, right? Steady flow analysis, and then from option go to flow distribution locations, right? And then you have to select this as many number as you can. I'm gonna select 10, okay? The left bank, right bank, 10. It will just divide this left bank and right bank as 10 segment flow distribution location, and then I can even select this thing as 10 as well. It doesn't matter because we already specified the global variable as 10 segment. So if you just click OK, then you have to even save the plan as, okay, save plan, I'm saving it. And if you run the model again, then what will happen, you'll see that, okay, it's gonna run. So that's why SMS and HEC-RAS, these models are pretty useful for any engineering analysis. That's why people are using that this type of softwares, this ACC or HEC softwares, because the runtime is pretty low. See, it's running within few seconds, right? And see, we are done with the run, and what I changed, you can see we have the same profile, but this time, see, if I change the variable and velocity distribution, and then if I click this one, plot velocity distribution, if I click OK, then you will see we have the velocity distribution, right? We have the higher velocity because it is a kind of bend. That's why you can see we have this outer, this is the inner bend, that is the outer bend, and we have the deep portion there, right? So we know that for meandering river, the deeper canal or the thalweg, the deepest point located at the outer bend. So here it is, and you can see the velocity is 2.2 meter per second, and this is how we can even calculate the velocity. And how can you even import or export different maps? So from here, if I just go to file, and if I copy the plot as clipboard, and if you open any Word file, right, you can even paste it, your report or your publication, whatever you need, right? You can do that. I'm gonna open a new one and see if I just paste it, it's looking like pretty good, right? And this is how you can add the plot, and you can even change your cross section by here. This is 13, and anywhere you can go and you can see, you can check, right? You can check and you can copy. You can go to file and copy to clipboard, and you can quickly paste it there, and you can see it is showing the date, and it is showing you the variables, velocities, and everything, and elevation and station as well. So this is how we can export, and you can run the model from the very beginning, right? From a generation of geometry, from survey data to run the model. In the next tutorial, what I'll show you, and you can even see if you go to view, and if you want to see the XYZ perspective plot, and you can see the three-dimensional plot in a two-dimensional system, right? You can even change the view. If it is not okay, you can even rotate it, see? And now you can see from the upstream to the downstream, right? And you can tilt it this way, okay? So that's that. We can do this way, you can see, and then that's the river flow is coming from upstream to downstream, and you can see the cross sections are changing, right? And you can even create animation, you can even run it, you can even, right, you can go from one section to another section. See, this is how we can go. So that's that. This is another view you can see all together. So I'll show you this thing in details in future videos, right? Even from this one, when we'll have more profile, more plan, then we'll even compare all together, not a problem, right? So that's that. And even for 2D model, we'll use this RAS mapper to even display our velocity profile and everything. I'll show you that one as well, right? We have GIS tool, and we can use that one. And then from help menu, you can even use different it's user manual if you want. So you have everything there, right? You can do that. So these are the options you have to even explore by yourself, but I'm going to show you only the basic thing, that how you can start developing or setting up HEC-RAS model from scratch. So that's the one way to set up. So we have one model that is basically 1D model with steady run condition for a specific location, right? For 100 year of return period of water level and flow rate. So in the next tutorial, I will even show you how to calculate these values, and at the same time I'll show you the breeze location, because we know we have the breeze, right? We have to insert the breeze. We have this option here, breeze or culvert. If I click there, it is asking where, right? Which one or which cross section will be our breeze cross section. We have to even specify everything. I'll show that each of these tools, and then our breeze section will be there, right? In between section number 4 and 3, right? There we have the breeze. So we'll insert our breeze, and then we'll insert the piers and everything, and it will look like a breeze, real breeze as well. Okay, and then we can even run the model. We can see there will be some velocity changes, and even though we are gonna calculate that scour at the end, hydraulic, we'll do some hydraulic calculation, and based on that we'll be able to calculate breeze scour. And what will be the scouring? There will be different types of scouring. From a breeze scour, it is called a pier scour from breeze pier, and there will be scour from abatement of the breeze, and there will be some local scour as well. So we'll combine them together and we'll add them up, and then we'll calculate the total scour, and based on that scour, if it's necessary, we'll have to provide some piling while constructing this breeze or not. So that's the idea. We have to be able to calculate everything. So I'm gonna finish off here, and you can try by yourself, and if there is any problem, let me know. It is pretty simple, and I'm giving you every data you need, and then you can try by yourself. And good luck for you with your new modeling tool and new learning. New learning is always challenging, but you have to be patient, and you have to continue, and you have to try by yourself. Then you will be able to run any model and will learn new thing. At the beginning, you may find it, okay, it's very difficult to find this option, that option, but within 1 month or within a few days, if you just use this repeatedly, then you can remember every options you have, right? And yeah, definitely I'll show you everything and what is the capability of this model. So using this HEC-RAS model, we can do steady flow, unsteady flow, even water quality modeling, sedimentation problem, and 2D flood modeling, scouring, everything we can do, and I'll show you that time to time. Okay, so that's that. Thank you very much for watching, and stay safe. See you in the next tutorial. Hi there, welcome back. So today I'm going to show you how to set up an unsteady flow model in HEC-RAS. So we'll use today's case, the study area I have selected. It is somewhere in Canada. You can see here in the figure that we have one lake, St. Martin, and another lake is Big Buffalo Lake. So these two lakes are connected by an artificially constructed canal, this one called Rich 1. So we'll have our survey data for this cross section of this lake and this canal as well. So the idea is to test if the canal is appropriate to carry water from Lake St. Martin to Big Buffalo Lake. And in the next part of this video, and I'll show you the sediment transport model for this study area. That's why I have selected, because I have the measured sediment data for this lake and the unstudied flow data as well. So I'll share with you the bathymetry or the cross-sectional data that I have, and you can open it and you can follow what I'm gonna do right now, so that you can learn how to set up any unstudied flow model in a HEC-RAS, because by this time you know how to create cross-section, right, from survey data if the data is in Excel file. In my first video I have already demonstrated that one, so you can go back to this video if you missed that. It is there. I'll give you the link, and I'll provide this link in the description below so that you can download this cross section and you can even import and you can test. Okay, so what type of data I have, and I'll show you that one. Let me quickly go back to this directory where I have this data, unstudied flow data. So I'll give you that file. Basically this one is a geometry data, and I'll give you this flow and sediment data as well. This data will be necessary for sediment transport model as well. So we have this type of flow data. We'll use this one today. We have the time series flow data. That's why it is unstudied flow data. And if I plot that, it is looking like this one. We have this daily data from the 31st of October 2011 to 31st of October 2012, right? So we have data flow rate in feet cube per second. That's why we have to use US customary unit. Okay, so let me quickly open HEC-RAS 6 version. This is the latest one, and I already demonstrated how to install, right, download and install HEC-RAS. So maybe you already have that one. So what I'm gonna do, I'm gonna create a new project at the very beginning, and I have to find where I have to save that. I'm gonna save everything there where I have that geometry file. It should be there within this HEC-RAS unstudied flow, and I'm gonna give the name as unstudied. Okay, unstudied flow model. Okay, unstudied flow model. So that is the name of my project, and if I click OK, it's gonna ask which one, right? Is asking about our US customary unit or not, because I'm gonna keep it. So US customary is our default one. And what I have to do, the next step is to create the geometry, right? You know that very well. So since I already have the geometry that you'll also have, I'll give you that. So I'm gonna click file, I'm gonna import that. I'm not gonna even waste time to import this data from Excel file, because we know how to do that, right? So I'm gonna import. This time you can't even open using this way. You have to import it, this geometry data. If you have this data in different GIS format or even different format, because this data is in HEC-RAS format. So I'm gonna click that one, and then you can see this right name of the file activated there. If I click there and you have to click OK, then it is gonna ask what will be the unit. We know, right? The unit is in US customary. Click next, and it is gonna ask you some other streamlines and other imports. I'm gonna click next, and then it is asking that okay, we have other stations and other informations and cross sections, breeze and everything, right? I need everything. Okay, and finish. I'm gonna finish it, and then we have this survey data, right? This is pretty appropriate we have. And if I just want to run this model for this one, we can do that. And even we can, what we can do, even we can interpolate if we need. But since this is artificially constructed canal, we don't need to even interpolate, right? We'll do that while running this model as sediment transport model. So the next step, we have this geometry, then we have to save this geometry, and I'm gonna save it as different name. I'm gonna give the name as unsteady, okay? Unsteady, wait. So unsteady geometry, okay? And that will be saved there. It will be there. Okay, so we are done with that one. So what I have to do, the next step is to create the flow data. So previously for steady flow data, what we have done, right, this one, steady flow data. But now what we have to do, we have to create this unsteady flow series, because the flow is changing with time. That's why it's called unsteady flow data, right? We know that if the velocity, flow rate, and the depth of water will change with time, then it is called unsteady flow data. Otherwise it is steady. So time is the main criteria there, okay, in terms of here. And if we wanna run the model as sediment transport with unsteady flow, then you have to run this quasi unsteady flow data, okay, quasi unsteady flow. So we'll do that in the next tutorial, next part of this series, in the next, okay, next time we'll see that, not a problem. So I'm gonna select that unsteady flow data. This time it is only the unsteady flow, pure unsteady flow model. And here it is for unsteady flow model. See the very upstream cross section, you can see that it is gonna give us, will provide our, if we click there, boundary condition, it is gonna give us these three options: stage hydrograph, flow hydrograph, and stage or flow hydrograph. So we have our flow hydrograph, right, the time and the flow rate. So I'm gonna click there, that one, and it's gonna open this one. So what we have to do, we have to select that start time, right? We can select that, or we can automatically get that one. How can we get that? If you want to select this way, we can get that. Otherwise there is another way to get it automatically. So that will be, I can show that one as well. So for the first time, I'm going to show you this one, not a problem. You have to select this one. If you select simulation time, then you have to fix your simulation time first, then it will automatically select the simulation time. But since I started with, right, flow data, so I'm gonna import my file first. So it will be 2011, and it is October, right, October 31st start time, and it should be 00 because we have the daily data, and you have to select that one as day. But you can see here it is gonna go up to 100, right? So you have to select the number of ordinates there, otherwise it won't create that 360. So how many we have? We need like 367, okay? Then we'll get the appropriate, right, 30, see, 30 first to that one, okay? And I'm gonna copy that data from here, only this column, because we already have the date column, otherwise it won't plot anything. And if you want to paste it, click there and paste it all together, see, and let me check it. Yeah, it's matching with date and time. And then if I want to plot it, it is gonna plot, and if it is okay, then it's gonna show the same plot we have in our Excel, right? These two are missing, that means it is correctly imported, the same plot we have here. That means our flow data is okay. This is the upstream boundary condition we have here, and what we need, right, I'm gonna click OK, and we already imported this one here, the upstream flow data. And what we need our downstream boundary condition there. So in order to do that, what you have to do, you have to click there, and then see, now we have another, you can even provide the same stage and discharge curve there, or flow hydrograph, or a rating curve, or normal depth. So for this case, I'm gonna provide normal depth. So usually what we did, or what we do, right, we provide this normal depth as a gradient or slope. So it will be 0, 0, 0, 2, 3. So you can use that same value I'm gonna use here. That is the downstream boundary condition. But for steady flow, what we did, we use known water level, right? We already calculated the flood frequency analysis. We perform that one, and then we find out, right, what is the 100-year retain period. But for this case, to be on the safe side, we are going to use this normal depth as our downstream boundary condition. So that is the normal practice. So keep in mind that one. Okay, so we are done with our boundary condition. We can save that on a steady flow data. So what will be that one? On a steady flow data. Okay, so that will be on a steady flow data. So we are done with this one. So it is pretty simple. The model, if you have the geometry, your model set off won't take that much time, but since the model is going to run for 1 year, it is going to take a lot of time. Okay, and then we'll see pretty nice plot this time and animation as well. At the end of the video, you can see that. So we are done with this one. We can close that. What next? So we need to even import our run condition, right? We have to generate that one. So we are done with our on a steady flow data. We're done with our geometry. We're done with our project. We need our plan, right? So I'm going to create this on a steady flow analysis this time. And when I'll run the sediment transport model, I'll do that. When I'll run water quality model, I'll use this one. And at the same time, I'll also use hydraulic design function to calculate the scour, right? Different types of scouring. We'll do that, not a problem. So this time it is only on a steady flow analysis. And what I have to do, I have to create the start time and ending time. So what is the date? It is 2011, and I saw that it is starting from October 30, right? I saw that the beginning is October 30 and the starting time should be 00 hour, and then ending time should be October 30, 2012. Okay, then we'll have the complete 1 year, and the ending time should be same. And then we have this one, and we can see the output options. You can select that one. The computational time interval is 1 minute. I'm not going to do that. I'm going to select it as 5 minutes in order to reduce the computational time, and you can use 1 minute. 1 minute is also good time. And what will be the output interval? 1 hour, right? And detail output interval. Okay, we can keep that, not a problem. Or even we can keep it as 1 day. That is also good because our time series is daily. And mapping output 1 hour, not a problem. And here, what we have to do, we have to even check this. Okay, it will check the geometry preprocessor if our geometry is okay or not. And then it will also check on a steady flow simulation. I'm gonna check that one. For sediment transport, we have to use this one, and it will do also the post processing. But we're not gonna select this one because this is basically for floodplain mapping. If you have any DEM data and if you run your model as 2D condition, then we need to turn this on, and we'll do that while running our 2D model using HEC-RAS. We'll do that in future videos, so don't worry about that one. So what we have to do, we have to go to option, and in order to check the flow distribution, right, as a nice plot, so we have to check, right, we have to change this to 8, or even you can change it to 10, 15, whatever you want. And this is the global variable I'm going to change. And then I have to save the plan, right? This is the on a steady flow plan. I'm going to save it. So what will be the name? On a steady, okay? On a steady flow. On a steady flow. And what will be the short ID? On a steady. I'm going to give on steady 01, okay? So that's it. And we are done with our plan. If I just try to compute, then it will check. If everything is okay, then it will start running, and it will definitely take a few minutes to run. I don't know how many minutes it will take, but let's check if it is gonna finish quickly or not, because I already just defined 5 minutes. So it's gonna run for entire 1 year, right? So let's check. It's gonna check. See, we have some error that interval for detail output is less than the hydrograph output interval. So we have to do that, okay? So you can check. It is very good model that is gonna give you everything, right? You can check it, and we have this problem there. So the time series data starts after the simulation starts. That means time series data starts after the simulation starts. That means our time series is not accurate, right? What you have to do, go back and check your flow data, This is how we have to be able to read, right? How to read this error and how to solve it. If you go there and if you just click there, you can see the time series data. It is October, right? It started with this one, October 30, 2011, and the date is this and the time is that, and ends October 30, right? There. Okay, so it's okay, and the simulation time, everything looks okay, and I'm gonna cancel it. So here it is. If you wanna change the run condition, there, we're done with this one, the run condition. Here, if I select not 30, we can select it like, oh, it should be 31st. Okay, it's 31st, and it should be 30. And let's see what we're gonna do here. And it's gonna be detailed output. Oh, this should be also 1 hour, otherwise that's why, because this time was higher than this time. And let's say I'm gonna save it, say plan, and let's compute this time. Yeah, hopefully it's gonna run. See, it's checking the geometry. If everything is okay, it started simulating. See, the time is gonna take, and you can see the time here, right? The time of simulation and the iteration it is doing. The first iteration we have, and we are not gonna run any 2D iteration here. If your model is for 2D, then it will show you the 2D iteration as well. The geometry preprocessor, it finished, right? So that's why it's showing finished, and now it's gonna calculate right on a steady flow simulation, and then after the simulation it will test that one on a steady post processor. So this is how it's gonna show you all these steps and calculation. And if you run your model for smaller time step like 1 minute, so it is gonna take a lot of time. And if you run the model for several years, so it will take more time than expected. So it depends on your computer speed and your RAM and as well. See, it's finished, and it's gonna show you the message that we are done with everything, right? So it's finished with 1 minute, and if you just reduce your time from 5 minutes to 1 minute, it will take more than 10 minutes to finish. Okay, then the number of computational time step will be like how many times? It will be 3, like it will be more than what we have here, multiple times than this one. So I'm gonna finish it here and let's check. Okay, I'm gonna just quickly show you the output of this model, and you can check everything there. We also have the same output, right? We have previously for each of this. You can see the elevation. These are in feet because these are basically in hill tracks. So that's why the elevation looks pretty high compared to our, and you can, right, the previous videos we saw. That is not a problem. And here, the most interesting part, we can see the cross section, right? Here we can see the cross section. And if you want to see the velocity plot, how can we do that? Here is the velocity plot. We can see that's pretty nice plot we have. And here, click there and go to options and the velocities. Not the velocities, the profile we need, right? The variables we have to, it's there. And then the profiles or velocity distribution. If it is there, it is already there. It's going to plot everything. So that's that. It's going to show you this velocity and distribution, right? And what happened here, because while running this model, let me check that. Here it is on a steady flow analysis. Maybe I didn't check that flow distribution locations. It's already there. Okay, it's already there. We have selected this one, that one, everything looks okay. Okay, so we're done with this one. So let me show you that the velocity we have here, and then maximum range of plot. No, we don't need that. We're done with everything. Okay, so we have this velocity distribution, and we can see here we have different options, right? Because this is the constructed, artificially constructed canal. That's why you can see the trapezoidal section, right? So basically for this type of canal or channel, we don't need that type of, these are leg section. So these are the artificially constructed canal or channel. We don't need basically that much interpolation because it is same for everywhere, right? So that's why you can see the velocity kind of same. Okay, so what next? We have to go to our profile plot, right? Here it is, and you can see the water surface elevation and other information, and I'm going to show you the animation right now. If you want to see, click there and it's going to open this window. It is going to start from the beginning, right? You can see on the right side, that is basically the left side of the plan, and the left side here in this plan, this is the big lake. So that one basically this Lake St. Martin, this one basically this is the big Buffalo Lake, and what is coming from this side in this plot. But in the geometry we saw that way, right? It was the opposite of that one. Not a problem. And if you want to see, that is the animation, right? You can see the time here, right? You can see the time. It's from starting to end. Can you see that? Yeah, it's pretty quick, right? And if you want to reduce the time, you can even select there, and you can even see minimize the time, and it will be like less than that. Okay, here it is. Maybe it is so slow to see animation speed. See, it's gonna show you the time. Can you see that? It is slow, right? Slowly increasing and decreasing if you want to see that. Otherwise you can increase the time, the speed if you want. If you put it there, it is gonna be speedy, right? See? So this is how we can see, and you can record. We have the option, you can record the animation here. If you click there, it will be recorded, and you can even display while presenting your project. So this is how you can set up any on a steady flow model. It is basically the boundary condition, nothing else. And you can even change your roughness, and definitely we'll test that in our sediment transport model, and we'll test different equation while running our sediment transport model. So that is another issue. So setting up the geometry sometimes takes time. Otherwise, once you have the geometry right away, you can set up your model and you can run it quickly. And another one is the time, right, we need. So what I'm gonna show you right now, I'm even trying to interpolate the geometry. We can do that. Otherwise, we can even run the model with lower time steps so that we can see what it is going to show you, and it will take a lot of time. Okay, I'll show you that one, not a problem. But before that, I can show you other necessary plots we need, right? The profiles we need, these are the profiles, because see, you can see the profiles, the long profile you have. Based on this thing, you can decide which one is the most appropriate one, and that is the rating curve we have here. And what else we need to do for unsteady flow? We can even see from the view the perspective plot, right? That is the most important thing we need to know. And here we can see that a lake, a big Buffalo Lake here, and on the left side you can see that St. Martin Lake, right? And you can change so that you can easily visualize. Okay, no, not this way, but we need to see, keep it that way, because okay, see, that is the actual scenario. That lake is pretty big. That lake is pretty big, yeah. So here it is, see, water is gonna flow from this lake to this canal, and it is similar to this plot, right? This one. So water is flowing from this Lake St. Martin to that bigger lake, you can see there. And then we have constructed that canal, and we're testing if it is appropriate to carry water without sedimentation problem or erosion problem. So we'll test that in the next part of this video, not now, but in the next part of this tutorial on a steady flow, because that is also on a steady flow, and we are going to run the model for the same condition. We just run this model, and we'll add our sediment data, because we already have our sediment data here. I'll give you this everything. We have this suspended solid, and we also have our bed material. We need that. Okay, I'm gonna upload this all together so that in the next video I won't need to upload it again. You'll have the geometry, you'll have this data, and I'll show you how to add all of them, and I'll run the model and I'll show you that. And here it is. If I wanna even animate there, you can see it's gonna show you the flow. If I hit it, right, see, it's gonna even show you the plot. See, it's increasing. It is gonna show you for 1 year. You can check the date. It is pretty fast, right? And water is flowing from left to right, and you can see the change in water level on this big lake. So this is how we can change your plot, and you can even record this animation, and you can show them, right, that okay, this is my model, and it is like a live model we have. But for a steady case, we won't have, right, this type of animation, because the flow rate is constant for the time period we have. We don't need to specify the starting time and the ending time. That's why that is called steady flow, and this is why it is called unsteady flow here, since we have time and the flow condition is changing, and it's basically varying with time. And there will be another flow condition, uniform and non-uniform. Definitely this is not uniform flow, but we can consider this one as uniform flow. For most of the open channel flow, we assume that okay, these are uniform or non-uniform. That is another part of discussion. So this is the way we can display our result. We can record, we can do this thing, we can do that thing, and we can even see our cross section. I already mentioned that one, right? Because we already have everything. See the roughness, and we can change the roughness and everything we have there. And even we can copy. So these are the artificial canal. So that's why we don't need different types of information, right? We have only 4 values, this value, that one, and this. We need only 4 points. Then it is kind of trapezoidal, and we know that, right? The equation for trapezoidal equation for trapezoidal cross section of a canal. So you can practice by yourself, and yeah, definitely it will work. I'll give you this geometry so that you don't need to even import all this manual job. You don't need to do that. And last time I'm going to show the effect of time step, right? That is what I was trying to say, that what will be your time step. So at the same time, you have to reduce the time step, and you have to improve the accuracy of your model prediction. So for this condition, we have our observed data, and we'll check with our observed data. And I'm not going to do that here right now. I'll do it for sediment transport model. We'll test because we have our observation sediment density, and we'll check if our model is working or not. That's why we'll calibrate our model. We'll do that. We'll calibrate our sediment transport model because we have our observation data. And here, the main thing we need to know, if I just reduce this time step from 5 minutes to 1 minute, right? And you can even go to 0.1 second. I'm not going to do that. So the default one is 1 minute. And if I run this, you'll see, right, what is the time step. And I'm going to hit, see, it's going to check the pre-processing. Everything is okay. It finished pretty quickly. There is no error, but you can see that it is not even gonna see 1st of November. It's just running for 4th of November. Can you see that? It's gonna take a while. And even though the calculation, because it is computer running with 16 gigabyte of RAM, and the ROM is pretty big, so that is not a problem. And the processor is Core i7, so it's still is taking a while. And you can even run this model if you're familiar with Linux machine, and if you have any HPC, high performance PC, and you can run that one as well. They have this Linux version of this software package, so you can run that as well. That is not a problem. So previously, can you remember that? What was the total computation time? I can remember it is 1 minute and 6 seconds, but this time I think it's gonna take a few minutes, so it will be multiple times. But for this regular cross section of the channel, you don't need that, because we're gonna test our cross section, right? That's pretty regular. So whatever time step is, it won't change that much. So that's why you don't need to even reduce your time step in order to increase your computational time, and it is just gonna create a bunch of data. Your output will be, right, output volume will be big. You don't need that, because it's gonna repeat the same thing, and we can see, right, pretty quickly we can see what will be the output of this, and we can see the animation as well. Then we'll be ended up with this tutorial. In the next tutorial, you can see by this time what we have here, right? We have the bed material, see the percent finer, and people just collect the bed material from multiple location, and then they use that sieve analysis to plot this, right, this graph distribution or gradation curve. And if your particle is so fine, then that sieve analysis won't be effective, right? That's why you need to do the hydrometer, right, analysis. That is another test for the finer particle that is smaller than 200 sieve. So you need that hydrometer test. So that is another use. And after that, see, we also have that flow, right? This is the flow rate, and we have this outlet like buffalo, the big one. The outlet of that, we have this total suspended solid milligram per liter. So we'll validate our model, we'll export the data from our model, and then we'll validate using these values, because these are the measured data. Then we'll also see the bed change, right, within 1 year after running this model with this bed material. What will be the effect? We'll check that, and then we'll make sure that, okay, this canal is gonna be stable or not. So depending on this situation, we can take decision, right? So see, still it's running, and maybe it's only the halfway, not even it's done. So can you see that when the time step is 5 minutes, it was like 1 minute run time, and when it is 1 minute, the run time is like more than 5 minutes or 10, I don't know, it is gonna be more than that. It's pretty fast, and still it's running. So when it will be done, then I'll show you the animation, and then you can check that there is not that difference between the previous one and this one. But for other cases, maybe it is useful if you have a natural canal or channel and you need to optimize, because these are basically the prismatic canal, the regular shape of the canal, right? We have it is artificially constructed, we call it prismatic canal. And if it is non-prismatic, means the natural canal, then you need to even use that minimum time step, then your model will be stable. So we have to test this time step. That's why I'm going to show you this one, because we'll use different time step for sediment transport analysis in order to make the model stable. Otherwise, when we'll add our sediment right data, then the model maybe it may be blow up, and there will be different issues. So that's why we have to test with different time step, right? Because it is solving the differential equation. Unsteady flow, for unsteady flow or steady flow, whatever it is going to solve that differential equation. And if our solver is stable, if the model is stable with the appropriate boundary condition, the flow data that we have provided at the very upstream and the normal depth at the very downstream, because it is going to match, right, the downstream boundary condition, it is going to create that one, 0.00023 from that upstream boundary condition. And in order to match that, see, it's this time, it's multiplied 5 times. That's reasonable. Okay, so I'm closing that one, and I'm gonna show you the animation one more time, and let's see what we can see there. If I run that one, it's gonna start from the beginning, and here it is. Can you see that? Yeah, see the flow rate and everything. It's gonna show you this way. So that is the output of this model. So there is no change, I can't see anything. If you can see any difference, let me know in the comment box. Then see, it's increasing and increasing because we have the peak, right? You see the peak, and the changes will be there when the peak will arise. So that is the impact of the flow, and we have to test the impact. See, drastically it increases because we have the peak. We can see that, right, in the simulation or in the data set, we have the peak there. So that's that. See, it's gonna increase, and now it is this one. The time is this after June and July, and then it will just reduce because after that we don't have that much flow. Okay, so I'm gonna end off here. So try by yourself. I'll upload this data, and then let me know if there is anything wrong, because that is the most complicated model in HEC-RAS, and the sediment transport, it will be more complicated. And then I'll show you in separate videos about how to set up any model that is water quality model. Okay, I'll do that, not a problem. So thank you very much for watching, and stay safe, and stay safe until then, and see you in the next tutorial. Bye.